I'm not sure whether my talk will be related with quantum gravity, but I hope it at least will be related with topology and quantum error correction. So this talk is based on my joint work with Gleb Kalachev. Let us go to the plan. So first, I will review classical and quantum LDPC codes. Then I will discuss some constructions related with them called lifted products. Then I'm going to discuss some more abstract stuff related with sheaves and local systems. And finally, I also talk a little bit about high dimensional expansion and product of codes. So let us start with classical and quantum LDPC codes. Okay, classical LDPC code is just a linear code. So let me, okay. So it's just a classical code with a sparse parity check matrix. So it means that we have a system of linear equations and we have a very sparse system of linear equations. By sparse, I mean that in each row and each column of this matrix H, we have only constant number of non-zero entries. As any linear code, it has some standard parameters like dimension and minimum distance. And the minimum distance has a very nice geometrical description as a minimal distance between different code words if we consider all the solutions to this linear system as some subspace in this Hamming metric space, where the distance between different bit strings is just a standard Hamming metric. So what is known about classical DPC codes? They were introduced in 1960s and nowadays are used almost everywhere. What is fun about them that we can construct them quite explicitly, and there are asymptotically good families which can be constructed explicitly. And by asymptotically good, I mean that the dimension and the distance grow linearly as the length of the code grows. And moreover, these codes also have a linear time decoding and encoding. And this latter result is mostly due to Sipser and Spielman. And so the idea, so it's like the main topic of my today presentation. So let me describe it. So the idea of this classical DPC code is as follows. So first of all, we have some graph. And we require that this graph will be a good expander. And we put our bits on the edges of this graph, and we also put some constraints, some local constraints at each vertex, and we require that each local code, local constraint, has sufficiently large minimum distance. And later I will tell more about what are particular requirements for this minimum distance. And if this distance is sufficiently large, then you can prove then that this code, so it's just a collection of bit strings that satisfy all the local constraints, is a good LDPC code. And I also forgot to mention that LDPC codes are usually represented by graphs, but these are slightly different types of graphs. So these are bipartite graphs. So we divide, so in one part we have bits and in another part we have checks, and we connect the check if it's, we connect a bit with the check if a bit is present in this particular check. Okay, what are quantum LDPC codes? So quantum LDPC codes, by quantum LDPC code in this talk, I mean CSS codes. And as you know, CSS codes are defined by pair of parity check matrices that define two classical codes. And we require that both these parity check matrices are sparse. And in this case, we call this a quantum LDPC code. So quantum LDPC code can also be represented by Tanner graph, but in this case, it has 3 parts. The middle part corresponds to the qubits, and to other parts corresponds to the x checks and z checks that are just standard poly operators that checks this quantum register. And as everyone knows that for a CSS code to work, so we need this equation to be satisfied. So which can be restated slightly different, that we have that orthogonal complement to the code CZ is inside the code CX and vice versa. Okay. Quantum codes also has similar definitions of the parameters. So they have the dimensions, they have the minimum distance, and here geometrical picture is a little bit different. So instead of individual bit strings, so we consider rather some groups of bit strings that form cosets. Yes, if we consider, so the best way, in my view, is the best way to look at CSS code is just to view it as a quotient codes. And in this quotient code, we have a group of bit strings, and the minimum distance of this code is just the minimum distance between different groups of bit strings. And the very famous example of a quantum LDPC code is a Kitaev story code. And as all we know, it is related with topology and more importantly, with systolic geometry, because the minimum distance of Kitaev code is just the size of the minimal systole. And the systole is the smallest non-contractible loop in this manifold. Okay. What are applications of quantum LDPC code? So, mostly people think that they can be very useful to design future fault-tolerant quantum computers. And a long-standing conjecture in this area was a so-called qLDPC conjecture that asked whether are there any good families of qLDPC codes. And now we know that this conjecture is true. Okay, let me very, very briefly discuss the history of this subject. So before 2020, all we have were the codes where the minimum distance was almost like square root of n. And then something magic happened in 2020. I don't know, maybe we should blame COVID for this, but several groups of people proposed some very new ideas and constructions, and till the end of the 2020, we already have new codes that have almost linear minimum distance. And in more recent papers in 2021, so in our paper with Gleb Kalachev, we finally solved this problem and showed that we can have good LDPC codes. And after that, a lot of people came into this field and proved many other things. And now we have linear time decoders, NLTS Hamiltonians, and geometrical local codes in finite number of dimensions, and many, many other things. And I should say that the main contributions here are related with the following 3 ideas. So the first idea, which is in my view is the most important one, is the idea of high dimensional expander. It was proposed in this set of papers. And the other 2 ideas are related with the tensor product, new tensor products of chain complexes over group algebras, and some symmetric Tanner codes. And these ideas were proposed in these papers. Okay, but let me discuss an idea of chain complex, which will be very important for my talk today. So a chain complex is just a bunch of vector spaces that we can view as some registers of bits and linear maps between these registers of bits. And we also require that the properties that two consecutive application of these linear maps gives you a zero. And this allows us to consider what is usually called binaries and cycles, and also define its homology group for each segment of this chain complex. And why chain complexes are so important for LDPC codes? Because they can be considered as a generalization of both LDPC codes, classical LDPC codes, and quantum LDPC code. So classical LDPC code can be just viewed as a two-term chain complex. Where one term corresponds to bits and another one corresponds to checks. And quantum LDPC code can be viewed as a three-term complex. And this condition, this CSS condition that we have, is exactly the same condition that we require for a chain complex. Okay. But how we construct more powerful chain complex if we have some component chain complexes? So the main idea here is to use tensor product. So what is a tensor product? So suppose we have two chain complexes. Yes, chain complex A, which we consider as goes vertically, and another complex B, which we consider horizontally. And when we multiply these complexes, so we obtain a new complex where each term of this complex is just a tensor product of the corresponding terms. And we have the following definition for the boundary map. And we combine the complexes that constitute the diagonal in one linear space, and these linear spaces form new chain complex. And what is important is that this idea is closely related with the Cartesian product of topological spaces, and even more important, it is also important with so-called Cartesian box product. So Cartesian box product is just a standard Cartesian product, but where we consider only objects that have dimension no more than one, so only graph, which is usually called a one skeleton. And this idea of a Cartesian box product can be used, for example, to characterize the Tanner graph of this chain complex that corresponds to the tensor product. Yes, if we have a Tanner graph that corresponds to complex A and complex B, then the Tanner graph that corresponds to the tensor product is just a Cartesian box product of these graphs. Okay, but let us go and discuss classical codes, and in particular classical product codes, which are also very important for my talk today. So given two linear codes A and B, so we can consider what is called the tensor product codes. So it's a code that consists of the matrices where each row, which column is from the code A and which row is from the code B. What is important that we can characterize this code in the following fashion. So if A and B is a parity check matrix for code A and B, then we can define this code using this set of equations. Yes, here W is a matrix, and if we multiply this W by matrix A from the left, then it is the same as we apply this matrix A to each column of this matrix W. And if we have a zero, then it means that this matrix A is a parity check matrix for the code A. And we can do the same by multiplying by transpose matrix B from the right. And in this case, we check that each row is from the code B. Why I'm discussing this? Because this is very related to the quantum codes, as we will see. Okay, So when we multiply this matrix V that we want to check whether it's code word or not, so we obtain two syndromes, the syndrome U and syndrome V. And what is important to know that these syndromes has some dependencies. And you can easily see this. If we multiply this syndrome, this matrix that contains this horizontal syndromes by matrix A, and if we multiply matrix V by matrix B, then we can check that we obtain the same, which means that we have a lot of dependencies between these syndromes. And this dependency allows us to define a new chain complex. And this chain complex is exactly the tensor product of two chain complexes that corresponds to the matrix A and matrix B. And we can easily check if we substitute this map, if we multiply this map by this map, yes, their composition gives us a zero map. So this is a perfect chain complex, and which means that we can define a quantum code, quantum CSS code. And so if we consider the second homology of this chain complex, and we obtain exactly this tensor product code. And if we consider the first homology of this chain complex, then we obtain exactly what is called hypergraph product code. And here in this hypergraph product code, so here in this part, we have code words, X code words, and here we have some degenerate X code words. Okay. But when we consider hypergraph product code, it is much more convenient to consider not to use matrix B, but to use the transpose of matrix B. In this case, we immediately can show that the code has a finite rate, and which means it has so the corresponding quantum CSS code has some non-zero dimension. And in this case, we also have a much more simple representation of this code, as you can see. It is well known that these codes can be used to construct codes with very large distances. And it was shown by Tillich and Zemmer that if we choose the matrix H of NKD code, then we obtain a code also with a minimum distance D, which means that if we use two good classical LDPC codes, we obtain a quantum CSS code which has a minimum distance that grows like square root of n. And the obvious question, can we generalize these codes to get LDPC codes with beta parameters? And the answer to this question is yes. Okay, but in order to describe this construction, I need first to describe the idea of lift. So first of all, we have some small graph which we call a base graph, and we assign, so we fix some set, which we call a fiber, and typically this fiber is just some group. And we assign to each edge of this base graph some permutations of this set F. And typically it's just a multiplication by the element of the group. And in this way, we obtain what is called L lift. So we obtain L times larger graph, and we replace each one edge with L edges, and we connect these L edges using this permutation. And this is what usually called in topology L-fold cover. And this idea of lift can be used to design codes. It can be used to obtain large codes from small codes. It can be also used to obtain large circuits from small circuits. So whenever you have a graph, you can use this idea. And what is important that if the base code is defined over the field of two elements, the large codes, it's naturally can be described by a parity check matrix where entries are from the ring, not from the field. Yes, and this ring is just what is called the group ring. And so it means that each element of this matrix is just a block, some permutation matrix. And we of course, the set of such matrices, we can add them and multiply them, and they constitute a ring. And this ring is usually called the group ring. Okay. The idea of lift is very important for to design classical DPC codes, and usually people use the following procedure. So we start from some requirements for our code, and first we produce a base graph. And there are some very smart algorithms to design the base graph. And then on the second stage, we usually obtain a large code, which maybe typically each size may be like 10,000 bits. And for example, and this base graph could be very small code, like 10 bits. And this large code is also designed by some very interesting algorithms, and I don't have time to describe them. And then usually people do in practice, they produce a lot of these codes, and then they just simulate them and compare and choose the best. This is a typical scenario how classical DPC codes are designed. And the natural question is whether we can apply this idea for quantum codes. And the answer is yes. And in order to use this idea, we just need to lift the product of two base codes. So I don't know how to apply the lift to arbitrary quantum code, but I know how to do it if this quantum code, which we use as a base quantum code, is a hypergraph product code. And actually, this is the main idea of lifted product code. So the idea is as follows. So it can be described in many different ways, but maybe the most simple one in this algebraic term. So the key idea is to go from the field to the ring. So we use exactly the same definition as before. So, first, let us start with the classical code for simplicity. Yes, we have a tensor product code, but in this case, we replace each bit with a group of bits. And we require that concatenation of these bits belongs to code A, and concatenation of these bits belong to the code B. So this is what is usually called in a classical coding literature a blockwise product code. And its formal definition is given here, and we use exactly the same formulas as before. And the only reason is that we just replace field with a ring. And we can also do this with hypergraph product code. Yes, we use exactly the same formulas as before. And we can define what I call a lifted product code. Okay. And this lifted product code, it is quite easy to check that it also has constant rate, because we just so in order to see this, so since if the corresponding hypergraph product code that if so the proof that this code has constant rate is exactly the same as for the hypergraph product code. We just count the number of checks and compare it with the number of qubits. But for the distance, unfortunately, we cannot do this in this very simple way. And we, in order to obtain codes with very large distance, we need something different, some new idea. And actually, this new idea is related with my today's talk. But before going into details, let me briefly describe this idea of tensor product codes. So as I said, so standard tensor products of vector spaces, it's very simple idea. So we have just a matrix, and the idea of the tensor product over group algebra, it may have some different descriptions. And for example, in the beautiful paper of Brookman and Eberhard, it was shown with some folklore results that it also naturally corresponds to what is called the balance product of G sets. So, and these sets can have some additional structure. For example, they could be topological spaces, and which means that this idea of tensor product of group algebras is naturally related with balance product. Okay, but in this talk, so we mostly consider them as just matrices. with a group of bits. Okay. And before describing this general idea of lifted product code, let us first concentrate on the very special case that was introduced by Kovalov-Pritko almost 10 years ago. And now they're also known as 2BJ codes. And so basically, it's just a lifted product code, but we instead of matrices, yes, we just use one-by-one matrices, just elements. And in this case, so if we apply this previous equation, so we obtain the following code with the following chain complex. And we can easily check, yes, that this chain complex is the correct chain complex. And what is even more interesting that if we try to draw the Tanner graph for this code, then we will have this structure, and this particular graph will play a very important role in the construction of good LDPC codes. And it's very fascinating that Kovalov-Pritko almost 10 years ago proposed something which is related with the final construction of good LDPC codes. And this graph is usually called, nowadays it is usually called left-right Kelly graph. And it has, it can be also described as a covering. Yes, and here I showed the lifts that we can use to describe this graph as a covering. Okay, and there are many examples of codes from this family. For example, the famous story code is just an example of this lifted product code. And the Hacht 3D code is also an example. And in fact, many other codes, like codes studied by Yoshida, they also can be described like this. And some other codes like quasi-cyclic generalized bicycle codes can be described like that. And the newest one that was studied by IBM is also from this family. And this family has a very nice properties. It has, you can easily check that this transformation is, so it converts the H matrix to HZ matrix and vice versa. So it's some automorphism that that this code has, means that this code has a transversal H gates, which is also very nice to have. Okay. But let me now describe in more generality this idea of lifted product complex. So first, as I said, we started from the Cartesian product of two chain complexes, and then we lift, yes, we apply covering to each component, and using these coverings, yes, we can obtain a new covering for this product complex. And this new covering has a very simple description. And before I describe it, let me also mention a very important property of these lifted product complexes. If we consider a vertex locally, and if we intersect it with a one-dimensional sphere, so you will obtain what is called in topology a link. And you can check that the link of a product of two graphs is always bipartite graphs. And square complexes that has this property are usually called complete square complexes. And since we apply here covering, so covering also, so if we had this property in our base complex, then we also have this property in its covering. And this is very important for all the constructions of good LDPC codes. And as I said before, so we have several geometrical and topological interpretations of this covering. So first of all, it's a covering that I already described. And it can also be viewed as a balanced product of two graphs. And it can also be viewed as a graph bundle. And what is also interesting that these ideas of the balanced product graph bundles, they were known for many decades, and people from quantum field noticed them only recently. Okay. And now we are ready to describe this left-right Kelly complex. So, and I should warn you that in the literature you can find two types of left-right Kelly complexes, and they are slightly different, but the difference is not that big. So the first type of left-right Kelly complexes is a balanced product of two Kelly graphs. And the second one, the one that appeared implicitly in the work of Kovalev and Pritchko, is a balanced product of two double covers of Kelly graphs. And this is a complex that we're going to discuss in this talk. And they have slightly different properties. And unfortunately, this left-right Kelly complex doesn't always have links which are bipartite graphs. So they're not usually a complete square complexes. But for this left-right Kelly graph, we always have this property. Okay. But let us describe the constructions that I usually call the expander lifted product calls. So the idea is as follows. So first, we design a classical LDPC code. And in particular, here we propose to use the Zemmer code, which is a slight variation of Sipser-Spielman code. So this is also a graph code. So the code defined on the graph, you place your bits on the edges and you place your checks on the vertices. But here the graph is a double cover of a Kelly graph, and it has a very simple description shown here. But it can also be described using a parity check matrix. And here I show you the parity check matrix. And for example, if we choose, if H is a parity check matrix of the Hamming code, then we have a very simple description. So you can see that the parity check matrix of the Zemmer code has a very, very simple description. And here I want to remind that the entries of this parity check matrix are from the ring. Yes, here the entries are from the binary field and here from the ring. Okay, and the idea is just to use lifted product constructions with these two matrices. And here I assume that the matrices HA and HB that I used here are different. And this is a very important assumption. Okay. Because a very naive idea is just to use the same. Yes, you can, for example, design one Zemmer code and use it 2 times. And in this sense, you will have an analog of hypergraph product construction. But unfortunately, lifted product codes are not like hyper product codes. They do not have this nice property that if we use good codes, a product of good codes, and we obtain also a good code. Unfortunately, it doesn't work like this for lifted product codes. And this is related with the so-called conjecture by Brookman and Eberhard, where they propose this idea that we can use tensor product of a code with its transposed version, and unfortunately this conjecture turned out to be false. And here you can see the counter examples that shows that these codes may have only distance which is only constant, so it doesn't grow. Okay, but let me describe how to deal with this problem. So now we have a problem. Yes, and let me describe how to deal with this. Okay, so first, these expander lifted product codes, as I said, they are used, they are based on this idea of lifted product, which is applied to 2 Zemmer codes. But how we choose these local codes, HA and code A and B? Yes, how we choose this local, this parity check matrices. And here the solution comes from the papers that proposed to construct qLDPC codes using high-dimensional expanders. And in fact, this idea is the most important one in all this construction of qLDPC codes. And it is intimately related with an idea that I'm also going to discuss briefly in the following slides, which is the idea of generalized high-dimensional minimal distance, some natural analog of the minimal distance of codes. And this high-dimensional analog of minimal distance of codes is naturally related with other properties of codes, so-called robustness and coboundary expansion. And the construction is as follows. So first we choose some infinite family of expanders. For example, you can use any family like LPS expanders, but you can also use some other expanders. It's not very important. But it is very important to use a pair of codes that has this this properties that is shown here, which we called in our paper product expansion. And if we have this property, and then it is possible to show that the quantum LDPC codes has a linear minimum distance. Okay, but let me also very briefly describe how all this related with locally testable codes. And if we consider our qLDPC code that we constructed by lifted product construction, so we can view it slightly differently. So we can also consider, as you saw previously, so this code is intimately related with tensor product, with this generalized tensor product, where we also replaced field by a ring. And this, it turns out that this tensor product, yes, it also gives you a very interesting code. And this code also, so this code has a very nice property that is called local testability, and such codes are called locally testable codes. And a good code is called a locally testable code if its syndrome grows with the distance. If you have a vector x and you calculate the syndrome, then the weight of the syndrome grows with the distance from this vector x to the code C. And not every good code has this property, but the codes that are constructed using this idea has this property. And this idea was also independently proposed by Dino et al. Also at the same time. And what I should say is that these codes, though they look differently, they are very similar. They have isomorphic Tanner graphs, but we just use some different interpretation of vertices. So, which means that we assign that. So we have the same graph, but we assign their roles differently. Yes, and here I showed how we assign the roles for LTC, and here I showed how we assign the roles in the qLDPC case. And in all these cases, you can use this left-right Kelly complex. Okay. And now, what are high-dimensional Sipser-Spielman codes that I was supposed to talk about? So first, let us consider the standard Sipser-Spielman codes, in particular this Zemer codes that I described before that are defined by this matrix. Yes, you have this graph, and you can also describe this as a code. So you have a bunch of bits which you place on edges of this graph, and you have, as I previously said, so you have some local constraints that are shown here. So in this sense, so we can view this code as a combination, as some hierarchy of local codes. So we have a very trivial local code that do not have any restrictions. So we just, so it's just a code that contains all possible values, 0, 1. And we also have another local code that is related with vertex. So the first local code was related with the edge. Yes, and the second local code is related with the vertex. So we have a hierarchy of localities here. And for two-dimensional Sipser codes, Sipser-Spielman codes that are obtained as a tensor product, using tensor product construction, we have a very similar idea, yes, but here we have more general hierarchy of codes. So here we have 3 levels. So the smallest level is the same. So it's just useless constraints for each individual bits. Other constraints corresponds to rows and columns of this local code. And another type of constraints is a constraint that that is applied to a matrix. And altogether, all these constraints, so we can view these constraints together as a as we constrain this section, this rectangular section, and we constrain it to be a product code. And here in this picture, you can see this. Yes, so we have constraints at each vertex, and each vertex constrains all the two-dimensional faces connected to this edge. Okay. And sorry, and what is the difference between the two types of Sipser-Spielman codes? That in one case, so we require that the local codes satisfy that this constraint. Yes, they should have minimum distance that grows sufficiently that has sufficiently good growth of the minimum distance. And if this condition is satisfied, then it is possible to show that this classical code is good. And the same can be said about this two-dimensional Sipser-Spielman code. If we require this constraint for two-dimensional distance, then we also can show that this code has LTC property. And in fact, if you want to construct quantum code, so you need to constrain not just these parallel codes, but also their duals. Okay, but let me now describe this idea of two-dimensional distance and how it is related with coboundary expansion and robust and agreement testability. So first, I should say that this idea was defined in our paper where we prove the existence of good qLDPC codes, and then it was further developed in the paper by Levier and Zemmer, where they significantly simplify this. And even after that, so in those two papers, this idea was even further simplified. And now we have a very simple definition. Consider this definition works not just for a product of two codes, it also works for product of many codes, but let us for simplicity describe it for two codes. So if we have two codes, so we can consider a chain complex. Yes, if we have a code A, the first code that is defined by generator matrix G1 and the second code that is defined by generator matrix G2, then we can consider this chain complex. And you can easily check that this is a chain complex. But this chain complex is a little bit useless in some sense because it's acyclic. So its homology is trivial. You can easily check it using just the properties that these generator matrices are full rank. So, and I forgot to say that they should be full rank. And we can, so the main idea here is to also, why we call it coboundary expansion and how it is related with expansion in graphs is because a product code can be also viewed as a Tanner code and bipartite graph. Yes, if we consider, so if we assign codes, if we assign codes to the vertices, code C1 to these vertices and code C2 to these vertices, then we can obtain a Tanner code where bits are on the edges. And you can easily check that this is exactly the tensor product code. And for this tensor product code, and we can try to apply the idea of expansion for standard graphs. By expansion, I mean the Cheeger constant, and we can try to apply it in these more general settings. So in the standard setting, so here in C1 and C2 are just repetition codes. And in this case, if we apply this idea of expansion, we can obtain just a standard Cheeger constant. But if we now consider more general situation, then you can check. I'm not sure I have time to formally show it here, but you can check that this this minimum distance that I described before, up to some normalization constants, is exactly the Cheeger constant. Is exactly the Cheeger constant of this bipartite graph. And this is actually the main reason why it is called a coboundary expansion, because it's just naturally generalized coboundary expansion of standard graphs. Okay, but if I have, I don't think I have more time. Maybe I just skip this section. Just briefly describe the idea of some other related idea, but not very related to this construction. So the idea of posets and the idea of considering posets as some topological spaces. So it turns out that all these constructions can be described as some sheaves that are known in topology on finite topological spaces. And finite topological spaces are the same as preorders, or if we also require T0 property of a topological space, then in this case, we obtain that a finite topological space is just exactly the same as a ordered set. So, and in this case, the topology base is just upper sets. And it is very cool idea, because you can naturally define and extend all the ideas from topology to these settings. For example, the Cartesian product of spaces it's exactly the same what is called the Cartesian product of posets. And for example, if we have a group action on a finite topological space X, then this is exactly the same that if we have a G poset, some action that works nicely with the order relation. And what is interesting that this definition of the balance product of topological spaces is exactly the same as the balance product of posets. And so we can define the balance product of posets. And why we are interested in these posets? This is because every simulation of a two-dimensional, for example, topological space can be also considered as a poset. Yes, you have three-level poset. You have level that corresponds to Z, level that corresponds to qubits, and level that corresponds to X. And you have order relation between them. And it is very natural to ask, can we use this idea to construct maybe new qLDPC codes? Yes. And the answer is yes, you can view. Moreover, this also gives us a way to treat qLDPC code as some kind of topological space. And you can assign to every Tanner graph of a qLDPC code, you can assign in a unique, almost unique way, what is called an order complex of the corresponding, this order complex, so X, so we can see the X as a poset, and we constructed order complex. And this order complex is a simplicial complex, so it's a topological object, yes, and we can in this way, so we can construct some topological spaces out of any arbitrary qLDPC code. And I should note that there is a different approach to this, and there's a very nice paper by Friedman and Hastings, and they show even not how to construct a topological space, but even how to construct a manifold from quantum LDPC code. And it is also quite natural to invert this idea. yes, maybe you can also try to start with a poset, yes, and then obtain this, its order complex, it's some topological space, and then interpret it as a qLDPC code, and you can obtain a qLDPC code. And it's very natural to ask, can we construct maybe some interesting qLDPC code of large distances from Posets? But I think I don't think that I have more time.
No, you
So
don't really have more
maybe
time.
we can stop. Do I have more time?
Your time is out, and we want to have time for questions. So
I think I'll prefer questions. Yes.
Really good a moment. Oh,
Okay.
you want to stop here or?
Yeah. I think I will stop here. That's more.